All right, let's talk about a new reaction called the halogenation. It's where we could add 2 bromines, or we could also add in 2 chlorines. Sometimes you'll see it as Cl2. So what happens here, let's talk about this as well. So let's talk about what kind of products we make. It's kind of hard to tell here, but we're going to do we're going to add essentially here. We're going to add, in this case, 2 bromines or 2 halogens. We're going to add 2 chlorines and 2 bromines. You can see that from the products. We have an alkene here. Add 2 chlorines and bromines. We are going to actually create it will be like a Markovnikov product. We'll see that in a different case. But where the things go, we Markovnikov. This is a regioselective reaction. Regioselective, and we'll see that more when we see the mechanism. And we also, hopefully you've noticed some of the stereochemistry here. It is a trans addition. It's a trans addition here. Trans addition. So you add 2 bromines, make a Markovnikov product. It's regioselective, and it is a trans addition. And there are no carbocations. You don't need to worry about rearrangements again. No carbocations. No rearrangements. So now it's just Br2 or Cl2. Now there's a similar but different situation. It's called a halohydrin. Now we have Br2 just like before, but we also have a solvent in the bottom of the arrow. In this case, it's a alcohol. It's methanol. So if we number our carbons, 1 and 2, if we look here, what happened? Well, we added. What do we add? We add in a halohydrin reaction. We add a bromine and the solvent. In this case, the alcohol. Right. We also make HBr. In both these cases. Right. We make HBr. So the H from here in one of the bromines ends up right here. We'll see that in the mechanism in a second. This reaction makes Markovnikov products. We'll see that in the mechanism as well. It's regioselective. So if you notice, what carbon does the solvent always end up on? The solvent always ends up on carbon 1, which of course is the more substituted product. More substitute carbon, that's Markovnikov product, and that's why it's regioselective. You'll also hopefully notice the stereochemistry involved here. The 2 products of this halohydrin, we get a trans addition again. A trans addition, and of course there are no carbocations, so we don't need to worry about rearrangements at all. So halohydrin, halogenation. Halohydrin, adding a bromine and the solvent. Halogenation, you add 2 bromines. So how does this work? Again, the pi bond is always your nucleophile, as always, and we're going to add 2 bromines. We're going to add them trans, which we talked about before. CCl4 is just a solvent that doesn't react, so it doesn't have lone pairs. We usually get a trans addition. The reason we do this, Br2, because this bromine is so big, it can be polarizable, where it can actually be, one of the bromines can act as a nucleophile, and we'll see that in a second. But the pi bond, of course, is the nucleophile as always. So what actually happens in this reaction, the first thing that happens is the pi bond electrons react with the bromine, and that breaks the bromine-bromine bond. And then a lone pair in that first bromine comes back down. This is really important. So the blue bromine, electrons are going to react with it, make a new carbon-bromine bond. The bromine-bromine bond breaks, right? So there's Br minus is formed. And then a lone pair in that first bromine, the first bromine comes back down and forms a new bond. And then you see it there. Now at this point, you've made a bromonium ion, it's called, a bromonium ion. Very similar to that mercurium ion, that 3-membered ring. And the Br minus is going to do an SN2 from the back side. It's going to react with either one of these 2 sides. Now, let's just say, in these cases it doesn't matter, but normally you want to react with the more substituted one. But in this case it doesn't matter, so you show 1, and the bromines end up being anti or trans to each other. We get that trans addition. Pi bond reacts, forms a new carbon-carbon bond with that bromine. Bromine-bromine bond breaks. Lone pair in that first bromine reacts down. You make a 3-membered ring, no carbocations. A plus charge on the bromine, no carbocations, no rearrangements. Second bromine, the other second bromine comes in, backside attack, SN2-like, you get the 2 bromines trans on either side. Just to emphasize this, we only get trans, so there is no carbocation. No carbocations. No carbocations. We only get trans products, so that's how we know there's no carbocation. We have that bromonium ion. So that was the halogenation. Now what about the halohydrin? Halohydrin in this case. So what if we have Br2 in a solvent? This time is water. So you make the bromonium ion, the 3-step arrows as we've shown before. The 3 arrows as we've shown before, and I'll do it here quick. So you have bromine and bromine. Draw those lone pairs in. First step, pi bond reacts. We break the bromine-bromine bond, and then a lone pair from the bromine comes back down and reacts there. Right? And that forms the three-membered ring. Now in this case, instead of having the Br minus react, the solvent reacts. Just because there's so much more solvent around than Br minus, even though Br minus is a better nucleophile. Lone pairs come there, SN2 style. We lose the H plus, the Br minus could have taken it, that's fine. And we get a trans Br to the solvent. We call that a halohydrin, trans Br to the solvent. Right, that'd be minor because there's so much more of this around. Now what happens if you have an unsymmetrical alkene? So if you have, in this case, carbon 1 and carbon 2, where carbon 2 is less substituted, where does the water or the solvent end up in these halohydrins? This is where it's This is where we call this a Markovnikov-like addition. Right, these halohydrins, or with the Br2, when it first reacts, you make a 3-membered ring. But just like as before, if you have two different substituted alkenes, or two different substituted carbons, right, from the alkenes, the nucleophile ends up reacting with the more substituted carbon, always with the more substituted carbon. No carbocation still, but you end up with a more substituted carbon. That's why we say it's regioselective and a Markovnikov addition. The thing you're adding, the second thing you add, ends up with a more substituted carbon. So let's take a look at this and maybe zoom in on the mechanism a little bit more. So we have a thing drawn here. So let's go carbon 1, carbon 2. I label these H's just so H, A, B, C, just so we could see them, maybe how the relationship stays the same or doesn't as things go along. So if you notice, H, B, and C are on the same side of the alkene, and they're both on the same side of the final product. HA and the methyl are on the same side. So you see HA and the methyl on the same side there. So what does the mechanism look like here? So remember when we make these bromonium ions, these halogenations, and there's no solvent around, so it's just bromine. So 3 arrows here. The pi bond reacts first. That breaks the bromine-bromine bond. And then the first bromine lone pair comes back and reacts there. And now, of course, this could come from the top or it could come from the bottom. So I'll just draw one just for the sake of making things simple for us to see. So the bromine now has a formal plus charge. It formed both a bond with carbon 1 and a bond with carbon 2, 1 and 2. HA and the methyl on the same side. So both those are wedged, sorry. HC and HB are both on the same side, they're both hatched. And we've made Br minus. Remember those carbons 1 and 2. Now if we look at these two carbons, carbon 1 and 2, 2 is more substituted. So that's the one that's going to be more delta plus. And that's going to be more likely for the Br minus to come and react. Right? We want to do the Markovnikovs. We react with the more substituted carbon. So it's going to happen here. We got to do an SN2 like reaction. You have go for the backside because that's where sigma star is at. That's where we get this trans products. Right? That's that SN2. Right? And so our product looks like HA, HB. One bromine is pointed up, one bromine is pointed down, methyl, and HC. And we'd also have the opposite, the enantiomer here as well, which would be, if I draw that quick. And then here you also have, I drew the enantiomer, which would be the exact same molecule, but switch the stereochemistry on this site where you actually made a stereocenter. This side too. So that's the mechanism for this. 3 steps, 3 arrows. Pi bond reacts with the bromine, breaks the bromine-bromine bond. Lone pair in the bromine comes and reacts with the carbon. We make a 3-membered ring, which we also make one from the top, and we then draw the one from the bottom. The Br minus, or if there was solvent around, that would react. The Br minus goes to the more substituted carbon, right? Just like we did before, or it could be the solvent. SN2 like, open that up. Things are trans to each other. the bromines or to transfer each other, and you also make the enantiomer as well. So that's halogenation and halohydrin mechanisms and details.